problem of the day for me. I'm pumped. All right? So it's an angular momentum problem. What that means is we got a disk. And it is 10 centimeters in radius. It has a mass 0.5 kilograms. It is rotating 24 radians per second. And it's rotating like a CD or a record or something like that, not on its end or anything funky. Okay? And it is a solid disk. Now, in a moment here, I'm going to drop it. I'm going to drop another disk, okay, that has half the radius, and it's going to line up edge to edge on the outside. Okay? The smaller disk has a mass of 0.2 kilograms. And the question is, what is the angular velocity going to be after I drop the second disk on there? Well, so we know that angular momentum is conserved. It's an angular momentum conservation problem. So let's figure out what it is initially. And that's going to equal I initial times omega initial. We already know omega initial, so we got to figure out I initial. Now we know for a disk, I is equal to 1/2 mR squared. In this case, that's going to come out to be 0.0025. Okay? Which means that I omega initial is going to be 0.06. Alright, so now let's look at what it is after we drop this second disk on top of it. Okay, the new thing, all it's going to change now, we got to figure out new I. Okay, now because with moment of inertia, we can just add two different modes of inertia. So we still have the 0.0025 from the old one. We're then going to add the new one. But you notice this, I say ICOM. I didn't bother with just saying I of it. We're going to have to add something else. Because it's not centered, we have to deal with the parallel axis theorem. All the parallel axis theorem says is that you got to add it. And you got to be like, okay, add ICOM plus how far off center it is. Okay? It's going to be 1 radius off center, so we add plus m times that distance it's off center squared. Okay? So we know that ICOM is again going to be 1/2 mR squared. We know that D is going to equal R in this case because it's off by 1 radius. So this simplifies to 0.0025 plus 3/2 mR squared, which comes out to be 0.00325. We then go back to our big, we want to conserve momentum idea. So we have L initial equals L final, which is going to be 0.00325 times omega final. So this should be able to solve to be omega final equals 18.5 radians per second, which makes sense that it would slow down because we've added another weight on top of it. You think, you know, I mean, you got something spinning and something jumps on it. Think of a merry-go-round or one of those like playground things. If you drop something on it, it's going to slow down a little bit. And that is an angular momentum problem.